So welcome back. In this video, we are talking about the design of rapid sand filter and the filtration operation of water treatment. Now, earlier we had discussed about the different design parameters of rapid sand filter. Now we'll assume the calculations here. We work out the calculations based on a small problem of designing a rapid sand filter for the raw water flow of 5 mld. So what we are having, the first step is the sizing of filter unit. So first of all, the backwash water should also be added here. So 2 to 5% is the range of backwash water, which should be considered as a part of the treatment treatment of the water by filter. So within the range of 2 to 5%, we take 3% here, and half an hour of working time for cleaning, and 24 hours is the working operation. So 23.5 hours is working and 30 minutes for cleaning of the filter. So water to be treated is this 3% should be added to the 5 mld. It becomes a 5.15 mld, so which is equal to 0.219 ml per hour, which is nothing but 0.219 million liters per hour. So filtration rate, if you assume in the range of 3000 to 6000 as 5002 liters per hour per meter square. So filter area is nothing but filtration rate is defined as what? Defined as discharge divided by surface area. So a surface area is nothing but discharge divided by filtration rate. So discharge is to 0.219 10 to the power of 6 divided by 5000, which comes out to be 44 meters square. 44 meters square. So this is less than 50 meters square of the filter bed. So maximum area for comfortable operations of the rapid sand filter is 50 meters square. So it is less than that. So it's all right. So now for working purpose, suppose we provide two parallel beds, and then what will happen here? 44 divided by 2, that's equal to 22 square meters, and the L by B range is 1.25 to 1.35. So within that, if we assume 1.33, and the dimensions of the filter bed are 4 meters and 5.5 meters. The depth of the sand is given as QD cube H divided by L into is equal to BI is a breakthrough index based on the performance under clogging conditions. So clogging happens, then ultimately what will happen? The load will improve. So because of that, the total discharge we are going to take as 2 times the filtration rate, 100% overloading. So 2 into 5000 gives 10,000 liters per hour per meter square. 10,000 liters means 10 meter cube per hour per meter square, because 1 meter cube is equal to 1000 liters. Size of the filter sand in the range of 0.4 to 0.6. I can assume here 0.6. And the terminal head loss is usually the total depth of the bed is around 2.5 to 3.5 meters, assuming that the maximum loss minus the depth of water in the filter bed. So it comes out to be around 2.4 to 3 meters approximately. So even if you take 3.5 and around 0.6 to 0.9 meters water depth, remove that, you'll ultimately get 2.5 to 2.7 meters as the terminal head loss. So we'll assume the head loss as equivalent to 2.5 meters and proceed. What is going to happen? So breakthrough index is a poor response of the filtration. We are assuming that within the range 4 into 10 to the power of minus 4, substituting to get the depth of sand is equal to 0.6 meters. The gravel depth estimation, we are having this formula. LG is equal to 2.54 K into log D. K is having a value of 10 to 12. So we can assume the KL is equal to 12, and D is the filter bed, the gravel size in mm. So if we assume that 5 layers of gravel are used, 2 mm, 5 mm, 10 mm, 20 mm, and 40 mm. So you are substituting that and computing here what you are going to get. For 2 mm, the depth of the bed is going to be 9.2, and for second one, 21.3, other one 30.5, and fourth one 39.7. For the last size, it comes out to be 48.4 centimeters. If you take the average of all these things, the average depth for each size comes out to be 9.8 centimeters. So you round it off to 10 centimeters so that you can provide the 10 centimeter depth of each size of the gravel. Total depth will be equal to 5 into 10, 50 centimeters. Wash water discharge, you have to calculate. So what is given as 0.6 meters per minute per meter square. So per meter is nothing but what you are going to calculate here. 60 centimeters per minute is nothing but 0.6 meters per minute. So 0.6 meters per minute. Now you are calculating it per 1 hour. So 1 hour means what? 0.6 into 60, 36 meter cube per hour per meter square. So wash water discharge in one filter. So this is per meter square. Already we have calculated the size of the filter bed as 4 meter width and 5.5 meter length. So area will be 4 into 5.5 multiplied with wash water rate 36 comes out to be 792 meter cube per hour. If we convert in meter cube per second, it is approximately 0.22 meter cube per second. So wash water troughs you are going to provide. How you are going to provide? That's another point of question. So this is your bed, right? So now, how many wash water troughs you can provide? So this is a total width of the trough is 4 meters. 4 meters here. Now I'm putting here 1, 2, and 3. I'm putting three troughs here. The overall length of 5.5 meter this side. This is the length of the bed, and this is the width of the bed on the other side, another side of the bed. So now what you are going to see here is you are dividing three wash water troughs. Each carries 0.0733. Let width of the trough also now assume 0.4 meters. So subsequently 1.376 b into y whole to the power of 1.5 is the formula we have, and q nothing but discharge through each wash water trough is 0.0733. So, and for b is equal to, we are trial and error basis we are taking here. So y is equal to 26 centimeters. So that is sufficient depth. It should not be more than too much depth. It should be shallow depth only, or at least you should have same width and same depth. So that trial and error we have to make. So now 26 centimeters depth is there. So 10 centimeter freeboard if you add, that is equal to 36 centimeters. So that means here, so this is your wash water depth, and this is the freeboard, right? Now depth of water in the tank. So range of water is now 1 to 1.2 meters. So that's why we are taking the overall depth as say 3.5 meters. And when you are taking the head loss, so let's assume that the water, the piezometers or manometers are connected at the bottom of the water depth. So that's why 3.5 minus 1, so 2.5 meters maximum head loss is considered. So let's assume 1.2 meter water depth and depth of 100 drain pipes. This is where some calculation is required. the total area of the perforations, because as I said, so you're having the laterals are there, and the main pipes are there, this side and this side. And this is the direction, let us assume that. So here you're having some perforations, you're keeping some perforations like this, and this side also you're keeping some perforations. This side also you're keeping some perforations, and this is the main diameter. So total area of perforation, it should be in the range of 0.2 to 0.3% of filter area. Suppose if we take 0.3% of filter area, so 0.3 divided by 100 into 4 into 5.5, it comes out to be 660 centimeters square, total area perforations. So this diameter we can assume. So range 5 to 12 mm size we can keep as far as the design calculations are concerned. So let us keep 12 mm dia perforations. Then in this, how many perforations we have to keep? That's what we have to calculate now. The area of the laterals will be is equal to 2 into area perforation, because this side and this side both we have to use. That's what we are going to take here. 2 into 660 is equal to 1320 centimeters square, which is equal to 0.132 meters square. So area of the manifold is nothing but 2 times the area of the lateral. So contribution is coming from to the manifold from these laterals and these laterals. Both sides you are getting. So contribution is coming from 2 times the area of laterals. 2 into 0.132 comes out with 0.264 meters square. So when you are calculating the average, the diameter for this area, it comes out to be 0.58 meters or 0.6 meters. That means, so where is this? Yeah. So the diameter of this particular manifold is 0.6. How we have calculated? The total area of perforations is based on the filter area, and based on that we assume some diameter of the perforations. Then we have calculated the area of laterals, calculated the area of manifold, 2 times the area of laterals. Once you calculate area of manifold, you have calculated the diameter of the manifold. So now after doing all the calculations, what we are supposed to do is come out with the final depth of the water, the sand filter. So water depth we have assumed as 1.2 meters. Sand depth you have calculated as 0.6 meters, and gravel you have calculated as 0.5 meters, and under drains just now is computed as 0.6 meters. So water is coming out at one side, and we will assume some freeboard here at 0.3 meters. So the total depth of the filter bed comes out to be 3.2 meters. The maximum size is 3.5 meters. So usually the head loss is calculated from the depth of the water here. You're connecting a piezometer or a manometer, one like a manometer, piezometer, and another one you are connecting at the layer, the under drains, because if there's a clogging, that clogging will affect here at the bottom. So you're keeping the second the manometer or piezometer here, and whatever is the value you are going to get, whatever is the value you are going to get, that is your head loss. This is a head loss. If there is a clogging, then ultimately what will happen is the head loss will keep on increasing. If there is no head loss, the water is freely flowing, then water level difference will be very less between the inlet and the outlet. So by looking at the head loss, we can understand where the filter is under clogging condition or not, right? So this is all about the design example for rapid sand filter.